So what we did previously was discussing the definition of cut, and the cut that we discussed basically was simply the count of how many edges cross the boundary between the partitions of nodes, or how many intercluster edges exist in the graph, assuming that each one of the subsets is one of the A's, where essentially a cluster. So if you assume it that way, you have that definition of a cut. Now we said we need to define something called an optimal cluster. Obviously, one approach could be to kind of find K clusters so that you have minimized the cuts. One drawback that can be shown has something to do with this is that it kind of tries to, it will have this sort of bias to choose clusters as small as possible, eventually even a single node. And to alleviate that, we have other types of definition, for example, something called a ratio cut. And the idea here, so let's first see how it is defined. It is going to be half of this sum. So again, we have the similar definition. So we have U and V's are a member set of edges. U is in AK, V is in the complement of AK, and you have this number here. The idea here this time is that you have this term as well. This means that if your clusters are going to be small with your K, this sum is going to be penalized, meaning that if you are trying to minimize this value of cuts, this time you also want to not really make your clusters too small. Now another approach is something called an Endcut. Before we do that, if you have one of these clusters, so if you have basically these clusters, let's say A1 to AK, the volume of any one of these is going to be, for each one of the nodes that belong in it, it's going to be the degree of those nodes. So it's going to be sum of the degrees of the nodes that reside within it. Now with this definition of volume, if you look at the definition of Endcut, which is again defined on this clusters, on this partitioning of the original set of nodes, you would have this definition. Again, it's pretty similar to the original definition of a cut. So again, on the denominator, you're going to have the same thing, U and V, set of edges, U and AK, and V belong to the complement of AK. And this is again the cardinality of the set. But this time, you penalize it with the volume of AK. So this time you want to pick clusters that have, nodes with higher degrees. So this time you're trying to kind of enforce a uniformity, meaning that if you have two clusters, like AI and AJ, you want, if each one of them have nodes in it, you want the number of adjacent edges to these nodes in these two clusters that you now have to find to be pretty close in some sense. Now let's consider a two-cluster approach, meaning we have one set of nodes and the complement of that set of nodes. And let's say we are considering the ratio cut on A and A complement. And let's say we want to choose A from the set of nodes such that this value here is minimized. Now let's do something that sounds a little bit weird here. And it's kind of like a reverse engineering this definition of the ratio cut in some sense. So let's say you define the vector A, which is a member of this space. So basically it has a value for each one of the nodes in V. Now let's say this is how you define A. So first you want to differentiate whether or not it belongs to A, or otherwise meaning it belongs to a complement. So here you would have this, and if not, you would have this. So whatever that it belongs to is going to go into the denominator. Now let's plug it in this definition, and we already know what this definition is. For each U and V of the set of edges, you have AU minus AV to the power of 2. This means what exactly? This means that if U and V both belong to A or A complement, then this thing is going to be 0. Now the only case in which it is not 0 is the case in which U and V is an edge such that U is in A and V is in a complement. And this time we're going to have AU minus AV 2. Now if we expand that, we have U and V an edge such that U is a member of A, V is a complement. So we know U is a member of that, so we have this. Sorry. We know this. Now if you expand this thing here, what exactly is going to happen? First thing first, you can factor out this part. What you see here is the definition of cut. So you have the definition of cut like this. This time what you have on this side of the curve, you have A plus this plus now what exactly is this value here? If you go back to the definition of the ratio cut, this is exactly transformable to that, meaning what? So this obviously is what? This is the cardinality of the set of nodes, it's the number of nodes. So if you bring this one into the denominator of this, what you will get is the number of nodes times ratio cut of AN, this. I want to go off on a tangent here and talk about something that is, I find it personally a little bit confusing, and it might be confusing for some of you as well. And that is has something to do first with the definition of cut. So first, let's kind of consider a simple example of a graph here. You have two nodes, one edge between them. This is node U, this is node V. Actually, let's not consider them U or V. This is node 1, this is node 2. And this is cluster 1, this is cluster 2. Okay. So the first thing we want to do is definition of cut on this. So it's 1.5 sigma kk. Let's call it, let's consider the first value first. So we first know that going to the definition of a cut, when we have A1 all the way until AK, we're going to have 1, 2, and for each one of these Ks, we want to count this. Okay. Now the important thing that I want to talk about is this. Consider this here a set, not an ordered tuple, meaning that the set of edges for this graph that I showed above is going to be this. You could consider it as a multi-set, but it could be like this. But now for this course, we show it like this, okay? Meaning that the order of these two doesn't matter. Meaning that when you're computing this value for each one of your clusters, when you're computing it for A1, you are considering all of the sets of elements in, E, in which one of them belongs to A1 and one of them belongs to something other than A1. Meaning that you are looking for tuples in which if you consider them ordered tuples, you are looking for them, tuples such that one of them belongs to A1 and the other one doesn't. So in this case, for A1, you have the value 1, and also for A2, which is the complement of A1, you have the value of 1. Such that to get the cut, you have 1 plus 1 times half, which is 1, which is the number of intercluster edges. Now, one thing to consider is that, again, for this simple graph, L is going to be D minus A, which is going to be, it's going to be 1, 1, minus 1, minus 1. Now, if you assign two values to this x1 and x2, you know that xt lx is going to be, again, for each edge, you're going to have, you know, xu minus xv to the power of 2. It was also another proof of the positive definiteness or positive semi-definiteness of L. Now, one thing here is that, do we consider UV and VU differently? The answer is no. For instance, let's just consider this example here. This symmetry is what causes actually this square root. So we have, again, x1, x2, we have x1, x2. If you multiply this time, this one first, you're going to have x1 minus x2. And then you're going to have minus x1 minus x2. And again, x1 and x2. You bring it down, you're going to get x1 times x1 minus x2 minus x2 times x1 minus x2. And again, this is the symmetry that causes that. So you factor x1 minus x2 out, you're going to get x1 minus x2, which is x1 minus x2 to the power of 2. So you're not going to have 2 times this. This is wrong. You're going to have only 1. So kind of consider those edges as ordered tuple in some sense. I think there's some sort of, you know, the definition of cut here is probably not very optimal, I guess, in terms of notation. So this is just something to consider as you're like going through these. So now we know that, at least for a 2-cluster format, with that definition of the vector A that we defined, ratio cut can be approximated with L like this, okay? Now, let's basically talk about the vector A that we defined before again. So let's define it again. So here, with this definition, if you belonged in A was in the denominator. And if you belonged in A complement was in the denominator. So that's this. And then we showed that ratio cut of A and A complement is this. So this is just the thing that we just mentioned. Now, some important properties of A are these. First things first, if you consider all of the nodes in V, and if you sum this value over the entire thing, this sum is going to be 0. The question is why? So obviously, based on the definition that we just gave, we are going to have A members with this value, and then we're going to have this many members with this value. And obviously this is just going to be this, which is 0. So the first property is that the summation of this attribute for all of the nodes of the graph is going to be 0. In other words, if you consider the all1 vector is going to be perpendicular to A, meaning that this would be 0. The other property, which is also fairly obvious, is that the L2 norm of A to the power of 2 is going to be the number of nodes within the graph. The reason why is, again, you're going to have this many members of A. So this was for basically all the U's that are member of A, and this is, remember, this was squared root, but this went to the power of 2, so this was this, which becomes this. Now, having this, the other one was obviously this, which results in this, which is this. So to sum up, this is 0, meaning that A is perpendicular to all one vector, and this is an equation that holds. So these are property 1 and property 2 of A. Now, what was the point of all of this? So we wanted to basically be able to rewrite the ratio cut minimization problem as a min cut problem. So as we mentioned, so ratio cut is going to be this times this. So this is based on the A definition that we described. So in order to minimize the ratio cut, you're going to have to basically solve this problem. So for this, you want to choose a partitioning that does that, such that this is like the first instance. So this is, again, the other one. So you want to basically optimize A, and A has these constraints. So basically want to pick the clustering in a way that this happens, which unfortunately is a NP-hard problem. As given the definition that we had for A based on the partition, we have basically a discrete set, and this discreteness is going to make this an NP-hard problem, which results in basically the fact that one type of relaxation that we could consider here is to kind of remove that discreteness assumption and work with continuous assumption instead, and instead basically do this. So we have like the same problem, we just relax it. This time we want to pick A, and such that this is 0. So this time we want to solve this one. And the solution to this based on Rayleigh-Ritz theorem is going to be the second, the smallest eigenvector of L. Now this is going to be a continuous variable, so when we find A, for each node U, if the value is larger than or equal to 0, we basically say that U belongs to this partition, and if it's the other way around, we say that U belongs to the complement of this partition. Now so this was for the min-cut problem. For Endcut also, we have like the second smallest eigenvector, again based on the Rayleigh-Ritz theorem, with the difference that the LRW, or the normalized Laplacian, is going to be used for that, which, as we discussed, was defined this way. So here I want to go on a tangent and talk a little bit about Rayleigh-Ritz. Not a problem, but basically Rayleigh-Ritz theorem and why it was used here. So we were talking about this value to minimize, and this is like going to be a special case of the Rayleigh-Ritz theorem, and we have L here, which is a symmetric matrix, and there is a theorem that states that it is unitarily diagonalizable, meaning that there is going to be a unitary matrix U such that you can define L as U lambda U transpose. So now if you consider the xt Lx here, you can say basically substitute that and have x U lambda ut, x transpose UUT. Actually, for the sake of argument, let's say that we work with this version instead. I mean, it doesn't really matter, it's just change of notation. So we're going to do this. So this is going to be the new way of announcing this, which doesn't really matter. So here, what we will do is that this time we are going to have this. So let's rename this. And given the fact that lambda here is a diagonal matrix with the eigenvalues, we are going to get sigma essentially we're going to have this. Now consider the fact that in this case lambda 1 is 0, so we essentially have this. And assuming that we were picking lambdas in this order, it's going to be larger than or equal to lambda 2 times y transpose y. And note that we picked y to be ux, so it will be equal to lambda 2 xt u t ux. And we mentioned that u is unitary, so this is going to be I, which is going to make this this. Now we know that xtlx is is larger than or equal to lambda 2 xtx when basically x is non-zero, and lambda 2 is going to be a pretty good approximation for the value instead. Now this version can also be generalized into basically, instead of picking the smallest eigenvector, you can have basically the k smallest eigenvectors of L, excluding the smallest. So given that we want like k clusters, the first step is to pick the eigenvectors corresponding to the k smallest eigenvectors of L. Now by putting these eigenvectors side by side, you can form a matrix called U. This would be your second step. Now third step is that, so U has this many nodes, okay? Sorry, this many rows. Therefore, each row is going to be corresponding to the corresponding node. So ZU would be U for every node in the set of nodes of the graph. Now one can run k-means on ZUs on this set essentially. Now this is an important thing. So we discussed the k equals 2 instance, and now we can discuss the larger numbers as well. And basically the spectrum of the graph Laplacian is pretty important because of this. It must be noted that there are close theoretical connections between spectral clustering and random walks on the graphs, as well as the graph signal processing.